Welcome back to The Explainer. Today, we're getting straight under the hood of OpenClaw's cognitive core to explore the Pi framework. If you've ever wondered exactly how an AI goes from a total blank slate to a fully context-aware assistant processing complex commands, well, you are in the right place. We're going to map out exactly how the engine thinks, streams, and delivers.
Okay, let's quickly run through our agenda for this journey. We've got 1. Inside the Pi engine. 2. Assembling the system prompt. 3. The core AI pipeline. 4. Streaming and boundary detection. 5. Gears of thought. And 6. A look at what's coming up next.
All right, let's dive right into part 1, inside the Pi engine.
So, this is where raw potential turns into actual, reliable utility. If you've ever worked with raw large language models, you know they can be, well, a bit chaotic. They hallucinate, they get stuck in weird loops, or they just hang indefinitely. The Pi framework actually solves these classic challenges by applying rigid, unbreakable structure to the AI runtime. It acts as a strict orchestrator, taking unpredictable inbound messages and transforming them into highly context-aware, safely executed responses.
Moving on to part 2, assembling the system prompt. Before the AI can even begin to think about a user's message, it absolutely needs its instructions. And we don't just hand it a generic set of rules. We physically build this system prompt piece by piece right as the message arrives. First, we inject its identity, its name and who owns it. Then, channel-specific rules. The etiquette for a Slack thread is way different than a WhatsApp voice note, right? After that, we hook in its diary of memory context, outline exactly what sandbox tools it can access, like Docker or a web browser, and most importantly, we lock the whole thing down with rigid safety rules. No self-replication, no power-seeking behavior. It's literally an entire customized rulebook generated in milliseconds.
Which brings us to part 3, the core AI pipeline.
Once that prompt is built, the message has to actually travel through the system. Picture this massive flow on a full-screen whiteboard. This is the core AI pipeline, the absolute lifeblood of OpenClaw. It might look a bit complex at first glance, but we're going to reconstruct this flowchart piece by piece so you can see exactly how data moves from a raw input to a polished output. So let's start on the left side of our whiteboard. A raw message hits the system. Let's say it's a WhatsApp text. Instantly, the channel plugin steps in and normalizes that data into a standard internal format. The system then quickly checks if this triggers an auto-reply, something that doesn't even need the AI to get involved. If not, it lands in the command queue. And this isn't just a messy pile of data. It's a lane-aware first-in, first-out queue. That basically means it neatly organizes concurrency so messages don't collide with each other.
Next, we draw a line to the actual execution phase. The queue drains and triggers the embedded Pi agent. This is where the magic we just talked about happens. The system builds that dynamic prompt, loads up the recent session history so the AI actually remembers what you were just talking about and fires off any pre-start plugin hooks. It's essentially telling the rest of the system, hey, the AI is about to start thinking.
From there, the engine routes directly to the LLM, like Anthropic Claude or OpenAI, and initiates a streaming call. Now, as the data streams back, the pipeline is actively watching. Did the AI ask to use a tool? If yes, it pauses the final output, executes the tool, feeds the result back to the AI, and just loops this process until a complete final response is ready.
Finally, we reach the right side of our whiteboard. The completed response flows out, triggering the message-sending hooks. It hits the specific channel outbound adapter, turning it back into that WhatsApp format, for example, and gets delivered straight to the user. The pipeline wraps up the whole job by persisting the new session history and firing the final end of agent hooks. It really is just a flawlessly choreographed dance.
Okay, let's head into part 4, streaming and boundary detection.
Let's put on our X-ray vision here and look inside that streaming LLM call we just mapped out. Under the hood, the streaming state machine operates on 3 core events. It fires a message_start event, which is followed by a continuous flow of message_update events. What makes this so incredibly powerful is that tool executions are perfectly interleaved within these updates. The system doesn't have to wait for the whole message to finish before triggering a tool. It grabs what it needs on the fly, all concluding with a cleanly wrapped message_end.
But let's be honest, absolutely nobody likes a bot that sends text one tiny syllable at a time, or worse, just completely hangs. To keep the user experience incredibly smooth, the Pi engine uses paragraph-level coalescing. It batches small chunks of streaming text together so they arrive in neat, readable paragraphs, Plus, it enforces a strict 15-second delivery timeout. So if a model provider gets stuck, the system just cuts it off, completely preventing your system from locking up indefinitely.
And this brilliantly illustrates one of the absolute coolest features, block boundary detection. As the text streams in, the engine actively reads and parses the raw data, strictly separating the AI's internal logic from its external voice. On one side of the stream, you have hidden think tags, where the AI is literally talking to itself, plotting out tool usage or reasoning through a complex math problem. On the other side, you have the coalesced final answer. The Pi framework ensures that you, the user, only ever see the clean, polished output, keeping those messy internal gears completely hidden.
All right, part 5, gears of thought.
Speaking of those hidden gears, let's talk about how much thinking the AI actually does. The absolutely crucial point here is that this internal reasoning isn't one size fits all. The Pi framework gives you 6 literal gears of thought to tune the engine depending on the task. Need a quick weather update? Just set it to off for 0 reasoning tokens and a blazing fast reply. Doing light data sorting? Maybe use minimal or low. But if you're having the AI debug a massive software repository or write complex code, you can shift all the way up to high or X-high. This unleashes a massive token budget for an incredibly deep, complex chain of thought process. It basically lets you completely control the balance between speed and deep logic.
And lastly, part 6, coming up next.
We've now seen exactly how the Pi framework intelligently, safely, and efficiently handles a single interaction. But an assistant is really only as good as its long-term relationships, right? So what happens over time? Take a look at this sneak peek of the system's memory architecture. It handles short-term session history, file-backed long-term memory, and even high-dimensional vector recall through LanceDB.
Which raises a massive question. If an AI is constantly talking, streaming, tool calling, and thinking in these deep X-high logic loops, how exactly does the engine magically remember all this context across thousands of messages without completely overflowing and crashing? Well, we are going to unpack the brilliant context compaction and memory systems in our next explainer. You definitely won't want to miss it.